Hey, good morning. So sorry for sometimes running a minute or so late. There's job talks. We have 22 job talks for CS that are always at 10 o'clock. So it's kind of my duty to attend, and I try to cut it close, but sometimes leave a minute later than I should. So actually, one thing I want to just briefly mention or talk about are the homeworks, just because. So especially for those of you who are undergraduates or new to graduate school, sometimes there's a lot of concern about whether you're doing things the right way, or like whether your performance is good enough, or exactly what I'm looking for. The truth is, the only thing that I care about is that you're learning something that's useful to you. And so our grading tries to reflect that. So if you do something, if you choose the wrong parameter, but your concept is correct, you'll get most of the points. If the parameter is incorrect and that shows you didn't understand something, you might lose a little bit. But most of your grade will just be based on, like, as far as the TA can tell, did you understand the algorithm? And also, especially if you're in a PhD program, then really grades don't matter at all. Nobody will ever look at it. In fact, you might not even put it on your resume. So don't worry about that. But for those of you who are undergrads, it might matter. So I just want to say, also, I try to design the homeworks in a way that you have to do some amount of exploration. So I try not to hand feed you how to do the problems, because really the way that you learn is in struggling through figuring out how you should do certain things. If I just give you like a step-by-step, like these are the functions you should use, and this is the equation, this is how you do it, all you would do is follow some mechanical process and wouldn't learn anything. So it's kind of intentional sometimes if things are a little bit vague, or if I don't tell you exactly how to do something. And what I want you to do is just to try your best to think through the problem and do something that makes sense. Okay. So today we're going to continue talking about a question.
Regarding the homework, since you mentioned it, the evaluation function was giving us not very coherent to performance output. In the sense that if I don't apply any map on it and I just feed it in the magnitudes, it was giving me a better. Actually, I tried a Laplacian over Gaussian, which was giving me a bad qualitative output, but gave me the highest quantitative output.
Yeah, so the question is that the evaluation function does not really reward thinning. It doesn't reward thinning your edges very much, and although I did require you to thin your edges. Yeah, so that's in part it's because there's another evaluation. So I created like a simplified evaluation tool that runs quickly. There's another one that runs on the original data set, but it does a bipartite matching between the edges you create and the ground truth edges, and it takes a long time to run. So I didn't want you to have to like sit there for like 20 minutes while it's running the evaluation. So I did like a quick approximation. But it's true also that many algorithms just produce soft edges, and they might still perform well according to that metric. But it's also important to know, or to have, I guess it's sometimes important to thin your edges depending on what you're using them for. So that's why I wanted you to thin them. So yeah, so we talked about fitting mainly, which is if you have some set of points or data, and you have a model, and you try to solve for the parameters of the model that fits your data. And we're going to continue that, talking about Van Sack, and also talk about alignment, which is the same set of algorithms, but in a case where the goal is to map one set of points onto another set, or to find the parameters of a transformation that best align your data. And then also give an example of object instance recognition. So in the last class, we talked about least squares fit. We talked about two methods for doing least squares fit. And least squares is actually the most common optimization algorithm that you'll run into. It's the core of many other optimization algorithms as well. So other algorithms will have like least squares as an inner part of the routine. And it's important to always have at the tip of your fingers the solution to least squares in an inhomogeneous system where you have ax equals b, and in a homogeneous system where you have ax equals 0. So the latter is solved with eigs. The first one is solved with just matrix inversion. So now we're going to talk about we're going to talk about ransack, and then I'll talk about iterative closest points. All right, so ransack. Ransack is one of the most useful algorithms that you can know. It's a very generally useful algorithm, not just in computer vision, but any kind of data science. So it stands for random sample consensus, and that's pretty much the whole algorithm, that you randomly sample points, fit a model, and see how many other points agree with it. That's a consensus. So the algorithm is that you randomly sample the minimum number of points that you need to fit a model. So if you're trying to generate a line, then it has 2 parameters, so you sample 2 points. If you're trying to, or you can fit a line with 2 points, so you sample 2 points. If you were trying to fit a circle with a center and radius, then you would, I think still maybe only need to sample 2 points. If you're trying to fit something more complex like a homography, then you need to sample 4 points. But the key is you want to minimize the number of points you need to sample. And the reason for that is that you're assuming if you're using ransack that you might have some outliers or points that are misleading, and you want to minimize the chance that you randomly sample one of those outliers. Then you solve for the parameters given your samples. Then you score according to how many other points fit your model or are predicted by your model within some epsilon, and then you just repeat. So independently, you keep on randomly sampling points, solving for the parameters, and then scoring. There are some variations on this, like aransack, that may make these samples non-independent or may automatically choose how many iterations to do based on your fits. But the general ransack algorithm is the one that's most important to know. All right, so sampling. So in this example, you randomly sample 2 points. Just completely randomly choose 2 different indices. Make sure you don't choose the same point twice. Then fit a line to it. Then you see how many points are within some delta to that line. And so the score for this fit would be 6, because there's 6 points that are within this delta. Then I repeat. So I randomly sample a new pair of points. I fit a line to it. I see how many points are within the delta. And so the number of points here would be 14. And so I'd repeat that many times. And then at the end of it, I would choose the line that had the most inliers. The number of inliers is the number of points that agree with a particular model. So it's a really simple algorithm. And if you don't have very many parameters, like in the case of a line fit, then it's going to be very fast, because you only need to sample 2 good points once out of all these iterations. So if you don't have, if only half of your points are outliers, then you don't need to sample very many times to have a good probability that at least one sample is good. So some questions that we need to address are, how do we pick all the parameters of this algorithm? So one is the number of points that we sample, and that one's pretty simple. You want to sample the minimum number of points that you need to fit your model. So if you've got 8 variables to solve for, and every point allows you to solve for one unknown, or you have 8 degrees of freedom and 8 points gives you 8 constraints, then you need to sample 8 points. But you don't want to sample any more than that. So you don't want to do a least squares fit. You just want to choose the minimum number of points that you need to solve for your model. Then how many samples do you do? So I'm not going to derive this equation, but it's actually not very complicated. It's basically just that you set some probability. So you suppose that you have some number of outliers, and then you set some probability that at least one of your samples will contain no outliers. So in other words, the chance that, that a given, let's say that the probability of an outlier is A, then the chance that that none of the samples will contain an outlier is 1 minus A to the S, where S is the number of samples. Because you have to independently sample like that's assuming sampling with replacement, which is a good enough approximation, since you usually have a lot of points. So, that means that every single time you choose a point that is not an outlier. And so then based on that, then you can extrapolate that to say, well, what's the chance that at least one of my samples has no outliers? And that leads to this expression. So you can choose n based on that. Or you can just say, I'm going to do it 100 times. You know, if you just have time, if you have plenty of time to spare, then you just choose a large number. So then the final one is to choose your distance threshold. So how close does a point need to be to the predicted model in order to be considered good enough? And that would usually be based on some kind of noise model. So if you're matching if your algorithm is trying to solve for some transformation based on SIFT key points, for example, there are experiments that show how accurately SIFT key points are located, maybe typically within like a pixel. And so you might say that my threshold is going to be 1.5 pixels. So as long as my model predicts where the corresponding point is to within 1.5 pixels, then it's considered an inlier, otherwise it's not. And then, as I said, there's algorithms that can try to automatically estimate some of these parameters as you run the algorithm. But they're more complicated, and the concept is pretty similar. So this is just showing, as you increase according to this formula, as you increase the proportion of outliers, the number of samples that you need to run increases a lot. So this is showing these numbers are the number of samples that you need to run. This is the number of parameters. So if you have if you have only 2 parameters, then even if you have a lot of outliers, you don't need to do very many samples. This is for a fixed probability of success. I think it's like 99%. So if you have if you need to sample many points to fit your model, and you have a lot of outliers, then you have a lot of samples. So Ransack, remember when we talked about the Huff transform, that it's suitable if you have like 2 or 3 or maybe even 4 parameters that you want to estimate. But if you had 8 parameters that you wanted to estimate, the problem is that then you have an 8-dimensional grid that you have to count model parameters over. In the case of Ransack, you can deal with more parameters, but you still can't. If your model has 100 parameters, then unless you have a very small outlier ratio, then you can't really use Ransack. So it's usually used in cases where you have somewhere between 2 and 10 parameters, and you have somewhere between 0 and 80% outliers. All right, so Ransack, the good things about Ransack, it's robust to outliers. You can apply it in many cases where you have more parameters to estimate than the Huff transform. And it's often easier to choose the parameters in the Huff transform. So for the Huff transform, you have to choose these binning parameters, which is kind of tricky. And for Ransack, all you have to choose is how many iterations to run. The more iterations you choose, the more likely it is that you'll have at least one good sample. And you have to choose your threshold, which is usually pretty easy to determine based on the application. And you have to choose how many points you sample, which is just given to you by the number of free parameters in your model. So in practice, if I'm running Ransack, I usually don't have to fiddle with parameters at all. I just know what it is based on the algorithm and application. The downside is that if you have a lot of outliers and a lot of parameters, then the computation can grow quickly. You need to do a lot of run iterations. It can also be sensitive to noise. So if you have outliers and you have a substantial amount of noise, then Ransack may perform poorly because the noise will kind of dominate over the outliers, so that even bad samples may get a lot of inliers, or even good samples may not have very many inliers. And compared to, one nice thing about the Huff transform is that by doing non-max suppression over your parameter space, you can instantly get many good hypotheses for different model fits. So you can fit multiple lines in an image, for example. With ransack, you have to do something a little bit more hacky, like finding your best fit and then removing points that belong to the best fit, and then finding the next best fit. And so you end up, if you want to find 10 models that fit different pieces of your data, then you need to run ransack 10 times. So it's not as good if you're trying to solve for multiple fits to different pieces of your data. So ransack is, the classic examples of using ransack are when you're computing a homography, which is the plane-to-plane mapping that you do for photo stitching, or when you're estimating the fundamental matrix, which is the main thing that you do if you're doing structure from motion and trying to relate two cameras from different positions. So I'll show you the second part of the line fitting demo. And let me, I somehow I think I just turned this off when I moved it. That's why I went black. That makes sense. So let me pull over my stuff. Right, so here's the ransack algorithm. Sometimes I think it is worth looking at code when it's simple enough. So I set number of iterations as 200. My threshold is 0.03. Then for k equals 1 to n, I randomly sample. In this case, it's line fitting, so just 2 points. There's a more efficient way to do it than ranperm and then take the first two, but this is a clear way. Then I compute the slope and y-intercept from my 2 points. Then I look at the number of inliers, which is the number of points for which y minus mx minus b is within threshold. I could have used the total least squares method, but I'm just doing this for simplicity. Then if the number of inliers is better than the best count, then I keep track of that. I keep track of the best count and what the inliers were. And then at the end of this process, I take the points that had the best, or for the best set of inliers, I do a total least squares fit to solve for my final slope and y-intercept. So let's see how that behaves with noise and with outliers. Oh yeah, I was doing some other stuff. All right, so we'll do total least squares for comparison, and let's just take out Huff for now and do ransack. All right, so I've got a small amount of noise. I've got 20 points, 20 outliers, and oh, sorry, you can't see this. Pull that over. You don't need to see all that. All right, got to pull these over. So this is showing the inliers and the outliers. Inliers are in green. And this is showing the fit. So ransack is nearly perfect. Total least squares is far from perfect because it's sensitive to the outliers. So if I run it multiple times, so again, ransack is pretty much gonna work almost every time, like probably 99% of the times with these parameters. Then if so then I can try to break it. So let's increase the number of outliers. So let's say I have 50 outliers.
How do you create an outlier?
I just randomly sample a point within that plot. So uniformly, randomly sample the position. So even with 50 outliers, I'm getting a pretty much perfect fit. Right? And then I can even try to increase it to, say, 80. So now, actually, it's still working really well. I don't know why. Oh, Okay, so I guess I'm generating, I guess we can see here that I'm generating a point between 0 and 1 on the x-axis and -1 and 1 on the y-axis. So that's why the line suddenly looks pretty weird, because it's plotting different scales of x and y. But you can see from the parameters that the -1, 1, -2.011. So even with 80 outliers, I'm getting a near perfect fit every time. And possibly at some point it'll break. So if I do like 95 outliers, so that means that there's only 5 points that are actually generated by the line, and 95 are not. So then you can see that it's not working anymore, because chances are there's probably a better line that was randomly generated. So the other way that we can look at this is the performance as a function of noise. So let's go back to 10 outliers. Or, yeah, let's go to 10 outliers, and then let's look at the noise as the noise increases. So now now Ransack is underperforming total least squares sometimes. In fact, let's just go to the other extreme. So no outliers. And significant noise. Okay, so now this is the situation where total least squares is ideal. So total least squares will tend to outperform Ransack in this case, because Ransack, the inliers that it counts will be sensitive to this level of noise, but total least squares will minimize the overall error. And if I increase the noise further, then total least squares will probably perform much better than Ransack. Right? So that's what we see here. Right? So least squares is great if you have lots of points that are noisy, but not complete outliers, have nothing to do with your model. Ransack is great if you have some outliers, but you don't have too much noise of the points that are correct. And then just finally, for completion, I'll do a couple runs with Huff. Right, so Huff, got my one more plot here. So you can see that it's having some trouble with the noise, but actually the peak is still pretty good. In this case, everybody's happy, more or less. So here you can see that Huff is having the same trouble as Ransack, that sometimes, because of the noise, sometimes the parameters that have the highest peak are not actually the correct parameters. And then if I go to the other extreme, then both Huff will not work as well either if I have like 90 outliers and almost no noise as Ransack. Yeah, so Huff has trouble if I've got an extreme number of outliers. Well, actually, it worked that time and Ransack didn't. Okay, they both have a lot of trouble if I have a really extreme number. Let me make it a little less crazy. So here now so if I do like 70, then there's 70 outliers and 30 points generated by the model. So they're actually both working pretty well. Okay, that's interesting. So I guess so it seems, I don't often try doing Huff and Ransack at the same time, but it seems, based on this anyway, like they're pretty similar in their sensitivity to outliers and also pretty similar in their sensitivity to noise. But they're applicable in different cases. So Huff is applicable when you just have a few parameters, where Ransack, here I only have 2 parameters, but if I had a lot more, I could still use Ransack, but I couldn't use Huff. Okay. So, all right, so now alignment. So alignment is the same problem. I've said this many times. We usually want to try to solve for some global transformation that accounts for most of the true correspondences, and the same things that are a pain for model fitting are also a pain for alignment. So, so let me just talk about what I mean by a transformation or global warping. If a global transformation is one that's applied to all the points in the same way, a local transformation, you would be applying a different transformation depending on where a point is. So we've talked about filtering, which is transforming or changing the values of the intensities. Now we're talking about changing the coordinates of an image. So if you make an image twice as big, that's changing the coordinates of the image. A pixel that was at 1, 1, or a pixel that was at 50, 10 will now be at 120. So it's a coordinate changing machine. And global transformation, which is what we're mostly interested in, is applied. The same transformation is applied for any point. And usually it just has a low parameterization, just a few parameters. And for linear transformations, which is also the class of most interest here, we can represent the transformation as a matrix. So some common transformations are translation. We are shifting the image or patch. Rotation, change of aspect ratio, which means it's getting wider or shorter. Affine, which is a mix of the rotation translation aspect and also skewing, which skewing is if it goes like that. And perspective, which is a plane-to-plane mapping, a mapping from one 3D plane onto another 3D plane. So, for example, scaling, the way that we would encode scaling is by multiplying all the coordinates by some common, number. So we could have uniform scaling, where we are multiplying both the x and y coordinates by the same number, or we could have non-uniform scaling. So we can write this as a set of equations. So for scaling, we could say x prime equals ax, y prime equals by, or we can write it in matrix form, which is what we'll usually do. And in this case, the equation would just be x prime equals a0 times xy, and y prime equals 0b times xy. Right? So it's the same equivalent matrix form of the same equations. So rotation can also be written as a linear transformation, which sometimes, when you first think about it, rotation is obviously feels nonlinear, and so you tend to think that it can't be written as a linear operation. But it's actually written as a linear operation of a 2-by-2 matrix. So it's not linear in theta, but it is linear in the cosine and sine of theta. So, so rotation means that you rotate all the points about the center. So rotation about a point would actually be a translation, rotation, and then translation back. So it's important to note that rotation is always about the center. If you just have a rotation matrix, you're rotating about 0. And so we can write this as x prime equals x cos theta minus y sine theta, y prime equals x sine theta plus y cos theta. And if you want to see how you can derive that, you can use polar coordinates to denote x and y. So it's just the distance r away from the center times cos phi, the original angle. Then if you add a theta to phi, and you use this trigonometric identity, then if you plug back in x for r cos theta and y for r, or phi, x for r cos phi and y for r sine phi, then you get this formula, which you can see is linear in terms of x and y now. So if we have cos theta and sine theta, then we can write this as a 2-by-2 matrix. So it's one subtlety is that if you try to solve for this with a system of linear equations, it's possible that you would get different values on the diagonal, for example, because then you'd be solving for it as like 4 variables. So often if you're solving for rotation as part of a system of linear equations, then you need to impose a constraint afterwards to map it onto the nearest true rotation, or use other tricks to make sure that you're actually solving for a rotation matrix and not a general matrix. Another way you could do it is to say that these are the same variable, and so this is AA, and this is B negative B. But then still, like, the sine and cosine might not correspond to the same angle. So even though sine theta and cosine theta are nonlinear functions of theta, x prime is a linear combination of x and y prime is a linear combination of x and y. So what is the inverse transform of this function? You can actually figure it out without doing any inverse in your head. It's a what?
The negative swap between the minus
Yeah, so the negatives of the sign swap, and why is that?
the inverse of this is the determinant is 1 by 1.
Yeah, okay, so one way, yes?
Can we also just put the thetas? Because theta is negative?
Right, so that's the way I would think of it. So the other statement was, can we just make theta negative theta? So yeah, so if you think about it conceptually, if I rotate this much by theta, then the inverse should be rotating backwards by the same amount. So if we just substitute negative theta for theta, then cos negative theta is cos theta, and sine negative theta is negative sine theta. So I just flip the signs of the signs. So another way to do this is to remember that for rotation matrices, the inverse is always the transpose. So that's an important fact to know. So R inverse is equal to R transpose. That's true for 3D rotation matrices also. All right, and then like a corollary of that is RTR is identity. Right, so here's all the basic 2D transformations. So we've got scale, shear, rotate, translate, and affine is just any combination of these. So affine has 6 free parameters, and so that means that you need to have at least 3 sets of corresponding points to estimate it, because every set of corresponding points gives you 2 equations, the projection onto x and the projection onto y. Affine is a combination of scale, shear, rotate, and translate. And also note that the way that we deal with translate is that we just append a 1 to the coordinates that we're transforming, so that when we do this multiplication, we get x prime equals x plus tx, y prime equals y plus ty. This is related to homogeneous coordinates, which we'll get into later, but we don't really need to address that yet. So then over here in the affine, we get x prime equals ax plus by plus c, and similarly for y prime. Right, so the set of affine transformations is an important class of transformations. With an affine transformation, you can map any triangle onto any other triangle. So it's used for like warping meshes, for example. And you can tell that that's true because since you need 3 correspondences to solve for the transformation, the triangle only is defined by 3 points. So any warping of triangles is covered by affines. So affine transformations are a combination of the linear transformations and translation. Translation is nonlinear because it's not just a function of x and y. It's x plus this tx. So for affine transformations, lines map onto lines. Parallel lines remain parallel. Ratios are preserved, meaning that if one line is twice as long as another line, then after the affine transformation, it will still be twice as long. And it's closed under composition, which means that you can multiply a bunch of affine matrices with each other. You need to write it in this 3x3 form, of course, to do that. And then you'll get an affine transformation out of it at the end. So in other words, you can compose a scale, and you can translate and then scale by multiplying a translation matrix and a scale matrix, and then you'll have an affine matrix. Or you could translate and then apply an affine and then translate back, and you can write that whole thing as one affine matrix. Right, projective transformations is the other broad class of transformations that's useful. So projective transformations are ones where I keep on saying it's a plane-to-plane mapping, which is often like this standard mathematical definition. But the mapping is what is often being mapped onto is the image plane. So it's a mapping, for example, if you have 2 photos taken from the same position, then you're mapping from one image plane onto the other image plane. Or you could map from, say, the wall onto the image plane, and that will be defined according to this projective mapping. So a projective transformation is more general than affine. An affine is a kind of projective transformation. You might hear projective and perspective fairly interchangeably. So the differences are that parallel lines don't necessarily remain parallel. So for example, if you're looking down a train track, the parallel lines of the train track converge, and you know they're parallel because the trains don't always crash on them. But in the image plane or in your field of view, they reach a point. Ratios are not preserved, so lines that are further away get shrunk. There's foreshortening. So you can't just tell the relative metric lengths of objects by comparing their 2D lengths, their lengths of the projection into the image. It's closed under composition, so I can compose a new projective transformation by applying a sequence of them. And models that change a basis is not so important to go into. One thing that is really important is that it's defined up to a scale. So here I've got, okay, so I don't want to go into this too much, but we usually model projective transformations in homogeneous coordinates, which means that I've got my original xy, and I've got some scale factor. And I'm always dividing, to get back to my regular Cartesian coordinates, I divide x and y by the scale factor. And so since everything is defined up to a scale, even though I have 9 parameters, I only have 8 free parameters. But I'll go into that in more detail once we need it, which is when we get into perspective geometry and camera geometry models. So just here's for your reference a table of a variety of useful transformations and how many degrees of freedom you have for each of those transformations. So and then this is saying what it preserves. So for example, translation preserves all of these things. Similarity preserves angles, parallelism, and straight lines. Affine, your angles can get warped, but it still preserves parallelism and straight lines. The only thing that the only simple thing that projective transformations preserve are that straight lines remain straight. So if you take a photo and there's a straight line in 3D, then it will still be a straight line in your photo, if your photo follows the projective model, which is the standard model. So let's look at a couple of examples of solving for these transformations. So one is I'll just do solving for translation, which is a pretty simple case. So here we're given matched points. So A1 matches B1, A2 matches B2, A3 matches B3. And I want to estimate the translation of the object. So if I know that all my matches are correct or correct up to some noise, I can just do this using a least squares solution. And so I would write down the transformation. So xib is equal to xia plus tx. Similarly for y. And then from there, I would write this down in matrix form. So if I've got, for every point that I have a pair of equations. And so then I get this coefficient matrix, and I get this right-hand side non-zero matrix. And so then I can just solve for that using pseudo-inverse. Or if it turned out to be a homogeneous system of linear equations, then I would solve for it using EIG. It turns out that in this case, the solution will just be the mean difference between xia and xib, right? Which makes sense. So the translation will be the average amount that the points shifted. But in more complicated transformations like affine, it's not so simple. So let's say that I have outliers. Then what would I want to use in that case? What are 2 algorithms? Right, Ransak's one. And the Huff transform is the other, right? So let's see, so how do I do this with Ransak? So I sample a set of matching points. So that means that I sample, here I've got 5 points that I think match. Some of them are outliers. So I choose A4 and A5 and B4 and B5. The indices are meant to indicate that they're corresponding. And I estimate translation between them. So I'll estimate some, so the translation that I estimate will be the mean of change in the, actually all I need to do is pick 1 point in this case. I only need to pick 1 pair. I put 2 boxes there for some reason. So let's say I choose A4 and B4. Then I estimate the translation as the translation between A4 and B4. I project all the points according to that transformation. So I move all the points in B, for example, by the difference between B4 and A4. In this case, that was an outlier. And so I would, not very many of the remaining correspondences would agree with that translation. So then I pick a new point. Let's say I choose A2 and B2. I compute my translation, which is the point at B2 minus the point at A2. Then I move I apply that translation to all the points in B2, and I check to see how many inlayers I have. How many of the points, transform points in B2 are close to their correspondence, how many of the transform points in B are close to their correspondences in A. I forgot that I'm supposed to use the pointer here for people watching the video.
So what do you mean a patch?
By a point, so these are actually just single points now. So there was a patch that was presumably used to find the correspondence. But once that is done, then I'm just thinking of it as a 2D point, where I think that this point on the object is the same as this point on the object in the other image. Yeah, good question. So the question was, am I talking about a patch? And no, I'm just talking about a point coordinate right now. But the patch would be used typically for determining if the points are likely to match. So and then I would repeat that n times. And then so then a more complicated case is if I have I might have many-to-many matches. So I could have multiple little cat dolls here and figurines. And then so I want to solve for all the transformations from one to the other. So for that, I could use the Huff transform. And so I would initialize my grid of parameter values, which means that I'd have a grid of translation in the x direction and translation in the y direction. Or maybe you would want to do translation in the y direction this way. And then every matched pair casts a vote. So for every pair of corresponding points, that will vote for some translation. And in this case, it will just vote for a single cell, because a given pair of matched points gives you one translation. Let me just illustrate this briefly, because my guess is that, although it's clear in my head, I'm not communicating it clearly with words. Okay, so let's say I've got, these are my images. Oh man, okay, it'll figure it out. And then I've got my 3 corresponding points here. So different shapes are, the shapes should correspond. Then I create my grid. So translation in the x direction, translation in the y direction. And this is discretized, meaning I break it into chunks. Then given a pair of points that correspond, say these triangles, I'll get some translation between the triangles, right? Some tx, ty, which is just this coordinate minus this coordinate. and that will make some prediction. It'll add a count to one of my cells. Then I get a different pair of corresponding points, the squares, and I compute the translation between them. And that will give me another prediction for the translation. And then I keep on doing that, so I get another one for this pair of points here, and that gives me another prediction. And so even if I have multiple, if I had multiple correspondences between different sets of points, I can end up getting a lot of counts into different bins. And then I would say if any bin has enough counts, then I consider that there's a match there. And then I can further test it by doing a least squares fit to the inliers. I'll do another example of Huff with the object alignment. So it's kind of, it's simple, but it's not necessarily intuitive because it's not the way that we're not used to thinking of points as voting for parameters. So, so now what do we do if we have no correspondences? Oh, question?
So the true least squares, the one that, that gives us a mean, this gives us the mode. Is that how things work?
Yeah, that's a good way to look at it. So the statement was that the least squares gives us, well, least squares is, in the case of translation anyway, least squares is saying that translation is the mean difference between corresponding points. And the Huff transform is the mode difference of corresponding points. So it's the difference that most of the points have. And so the mode will be robust to outliers while the mean isn't. It's a good insight. I mean, the solution won't always be a mean, but that's still like kind of a good way to think of it conceptually in general. Okay, so what if we have no correspondences? Then obviously, like none of these algorithms apply because you need corresponding points. And if I were to randomly create correspondences between all pairs of points, none of the algorithms would work because I'd have way too many outliers. So for that, so if you want to align but you have no matched pairs, then Huff transform and ransack are not applicable, nor are least squares or anything else. Well, not anything else that I've talked about so far. And this is true for many important applications. So for example, if you want to line up two medical scans, you might not have an easy way of finding corresponding points, but you want to like align the intensities of the two scans or something, or a correlation of the intensities as closely as possible. Or for robotics or other graphics applications, you might have two point clouds, like a point cloud of a model and a point cloud of a laser scan, and you want to match them up as closely as possible, but you don't have a really good way of establishing correspondences a priori. That means ahead of time, between the points in the laser scan and the points in the model. So for these things, we can use what's called the iterative closest point algorithm. Is there a question?
You can use it even for maybe for 3D construction from 2D to 3D, right? Transact, if I'm correct. If you have two different points at different, if you have two different images at different point of time, you can use point-to-point matching and try to reconstruct the 3D.
For ransack.
Yeah.
Right. So ransack is definitely used if you have two images and you're trying to estimate 3D points from those images, then ransack is really useful because you can establish correspondences based on the patches around the images. But I'm saying if you just have a laser scan and then you have a CAD model, then it's not easy to create correspondences between them. And then like if you can't create the point-to-point correspondences, then you have no basis for ransack or the other algorithms. Right, so that brings us to iterative closest points algorithm, which is our last alignment algorithm. So here the goal is to estimate a transformation between two dense sets of points. And we're going to say it's from set 1 to set 2. And the algorithm is really simple. So you initialize a transformation. For example, you just center one set onto the other set. You might transform them both by subtracting the mean and dividing the coordinates by the standard deviation. I'll show that in a second. Then you assign every point in set 1 to its nearest neighbor in set 2. So for every point you find in set 1, you find the closest point in set 2. Then you estimate the transformation parameters, assuming that those correspondences are correct, for example, using a least squares solution. Or you could even use Ransack or something that's not sensitive to outliers. Then you transform the points in set 1 using the estimated parameters. So you shift all the points in set 1 according to that transformation. And then you, again, find the nearest neighbors, estimate a transformation, apply it, and then keep on repeating that. And you'll find a local minima. So there's just one thing that I want to spell out a little bit more, which is that initial transformation. So let's say that your one set of points in one image, is this visible? Yep. So let's say that these are your points. Right? So if I skip that initial transformation step, then what will happen is that all the points in the upper left will be closest to these 2 points. And so I'll say that all of these points are matched to each of these 2 points. And then if I'm solving for a general affine transformation, I'll basically squash my circle in the upper left so that it just like projects onto these couple of points. And then I'll be stuck. Then there's no like local improvement I can do. So you want to initialize by just solving for the mean and scale of your points. So one way to do that is that you first say that you compute the mean x, mean y, which is the mean of the x-coordinates, mean of the y-coordinates for this image. And you solve for the standard deviation of the x-coordinates and standard deviation of the y-coordinates. And the same in this image. So mean prime x, mean prime y, standard deviation x prime, standard deviation y prime. Okay. So this is just in MATLAB mean and SDD, for example. Then I want to use this to get an initial transformation that maps these points in set 1 over to the points in set 2. And so in order to do that, I want to subtract my mean from 1 and add the mean in 2. Divide by the scale in 1, add the scale in 2. So I can do that by so I translate, so let's say I've got some point over here. So I want to first translate it so that the center of these points will be at 0. So that'll be, 1, 0, negative mu x, 0, 1, negative mu y. Sorry that I'm writing really small. And then this is a 1. 0, 0, 1. So this matrix will translate all of the points in the first set so that their center is now 0 by shifting them all by the negative mean. Then I want to scale them all so that their standard deviation is 1. I should have written bigger. But this is 1 over standard deviation of x, 1 over standard deviation of y. And remember the 0, 0, 1 so you don't end up with an inconvertible matrix. So this combination of operations will now make set 1 so that it's in the center and that the average distance to the points is about 1. Then I want to shift it back to the center of set 2. Or actually, I want to scale it back to the scale of set 2. So I want to multiply by sigma x prime and sigma y prime. And then finally, I want to shift it back so that the center is the same as the center of 2. So now I want to add mu x prime and mu y prime to their respective x and y coordinates. And so this will be my x transform 1, x transformed 1 and y transform 1. That t there, I mean transform, not like not transpose or x to the t. Right? So at the end of doing all that operation, these points here will now be in like the same general circle as the points on the right-hand side. So you need to get your points into a good, you need to get at least like the very rough solution to the alignment before you can start. Or like if you're doing this using a program like MeshLab or Cloud Compare, you'll often manually shift one set of points and rescale it so that they roughly align visually, and then you'll run ICP to refine the alignment. So in this case, we would find the nearest neighbor for every point, compute the transform using the matches, a translation, the average difference between the corresponding points, move the points using the transform, and repeat until convergence.
So are you comprising all the transforms that could happen there, or just translation and scale?
So in this case, so you always have to choose your model ahead of time too. So in general, maybe I'm trying to solve for an affine transformation, but here I just said, let's suppose that, as a first guess, let's just say that it's a difference of scale and translation. And so that'll get me in like the rough general area. And then once I'm in the rough general area, then I can try to solve for the more complex transformation.
If you widen both the directions, then you might just lose rotational information, won't you? Suppose I have an oval shaped thing which matches to an oval shaped rotated thing, and I've widened them to a circle, then I've just lost the information rotation, haven't I?
Yes. Yeah, so the statement was, if I do it this way, then if I started with an oval that looked like that, and the other oval was just rotated, then I'm going to turn this oval into like another one, and then I'm going to think. So that's a case actually where the affine transformation is somewhat ambiguous, that you could find a correspondence either by flattening your oval or by rotating it. And so you need to know, in cases especially, I guess like the moral of the story there is that you need to know what is like the appropriate transformation that you should be applying. And also when you're doing this initial transformation, what is like what's an appropriate initial transformation. So if you think it might be only a rotation or a translation and rotation that relates them, then you might want to restrict your model to that and not allow it to scale independently. Or you could just say that I'm going to apply uniform scaling, and then that might help. So here's an example. This is one of your homework problems. So you extract pixels, P, so I've denoted them as P and Q. So you extract all the pixels that are non-zero, for example, using find in MATLAB. Compute the initial transformation, which is the math that I just went through. Get nearest neighbors. So you find for every point I, you find the nearest point. For every point pi, you find the nearest point in qj. There's efficient ways to do this in MATLAB as well. I think like is it D? I forgot what the function is. But anyway, there's fast algorithms for computing distance transforms in MATLAB. It's called a distance transform, but I forgot the function name. BWDist, maybe. Then you compute a transformation based on the matches. You warp the points in P according to T, and then repeat until convergence. And you can choose which model you want to use. If you want to do, say it's an affine transformation or a scale translation or whatever. All right, so ICP, what's nice about it is that it's really simple. You're just, every iteration, you find the nearest points. Those are your correspondences that you'll pretend are true. You compute a transformation, and then you apply it and repeat. So you don't need any correspondences. But this also has its limitations, so you need dense points. If you only have sparse points on two models that you're trying to align, then the problem is that that there may be no correspondences in those sets, so you might not be able to get a good alignment. It's also, the main problem is that it's subject to local minima from initialization. And so there's other methods that use ICP as part of its inner step to try to more robustly match sets of points. So one I link to later and one I link to here. So this one here does a branch and bound on the initialization and then does ICP within each node of the tree.
Example, like when you're at the runway, taking a photo of the plane taking off, the background will stay the same. So how do you determine the standard deviation of the background and which is standard deviation of the plane? If the plane will get smaller as it flies off, but the background stays.
Are you talking about this?
Yeah.
You're hallucinating a lot of stuff in there. There's just a set of points. But so I think, so the question was, all right, so if you have a set of background points, like how do you deal with those background points? So I'm assuming in ICP that you're only that you've already isolated the points to the model that you're interested in. If you have background points, then they're essentially outliers. And then you need, instead of doing a least squares fit, in that case, you could do Ransack or some other robust least squares that tries to deal with outliers. Yeah, but yeah. Okay, so all right, so this paper, this does the branch and bound, and this is just some examples from that paper that even with very different initializations, so this is the initialization, this is using ICP, and you can see that it didn't find a good fit because it started from a bad initial solution. And this is using their method, which is guaranteed to give you the globally optimal fit if the right distance measure is least squares. So this measure finds really good fits even if you don't have good initializations by doing branch and bound on the starting point. So to summarize these algorithms, we've got a least squares fit. Nice thing, we've got a closed form solution. It's robust to noise, but not robust to outliers. Robust least squares improves the robustness to noise, but it's slower. You have to do an iterative optimization. Huff transform is robust to noise to some extent and to outliers, and you can also fit multiple models, but it only works if you have a few parameters. Ransack, I said it's robust to noise there, but I would say it's robust to small amounts of noise and to outliers, and it works with a larger number of parameters. And iterative closest point only makes sense if you're doing alignment, not model fitting, and it does not require initial correspondences. So then in the last 10 minutes, I'll talk about object instance recognition. One thing to note is that I often stay after class and answer questions, but this class I can't stay after because I've got a thesis proposal to attend at 12:30, so I have to go right away. Okay, so object instance recognition. We want to try to find, we've got some image of an object, and we want to try to find another example of that object in a database. And by instance, it means that it's the exact same object. So I'm not matching different kinds of cars. I'm matching my specific Toyota sedan in one image to that same car in another image. And we'll assume for now that it's seen from a similar viewpoint. So it might be some rotation, translation, scale, but I'm not looking at a completely different side of the car. So the general solution is that we have to match key points to the object model, which we talked about before when we talked about SIFT. We solve for the affine transformation parameters, which is what we've been talking about today. And then we score the inliers and choose a solution with a score above threshold. So just to give a summary of the algorithm, I have to do some kind of key point matching, which means that I find a set of distinctive key points, define a region around them, extract and normalize the region content, compute some descriptor, and match the local descriptors. So typically you would use VLFeat and use like SIFT or some other existing feature matcher. And then at the end of this, you would get a set of features for every image. And then after running your matcher, then you would get a set of putative, meaning hypothesized correspondences between points in each pair of images. So after I've computed my features and I've got my input image, then I need to go through every image in the database and find possible correspondences. So for every database image, I find matches. Then the matched points, given a pair of matches, remember that with SIFT, you find a point in position, and you also estimate a scale and an orientation. So every pair of matched points, for example, these two yellow circle arrow things, gives me some guess at the position, orientation, and scale. And so I can vote for, given every match, I can vote for the position, orientation, and scale that relates an object in one image to an object in another image. So I find all the triplet, or all the sets of parameters that have at least 3 votes. Then compute an affine registration. So I'm then computing a more complex registration. I need at least 3 points to do that. And then see how many inliers I get. How many points agree with that transformation. And then finally report that I found an object if there are at least T matched points. So I'll go through this in a little bit more detail now. So first is the matching. So I want to match key points between a query image and a stored image that may contain the object. And so I've got my set of SIFT descriptors in each image. For each descriptor in the input image, I compute the distance to all the descriptors in the second image. And then if the closest of them is much closer than the second closest, then I say I have a good match. That was the ratio test that David Lowe came up with. And so, for example, if the closest key point to a given key point, if the closest key point in the second image is at least 80% less distance, or is less than 80% of the distance to the second closest key point, then I say that I have a good match. And this will get rid of most of the false matches that just the nearest neighbor would, while retaining most of the true matches. Note that this version of the algorithm I'm giving you is kind of the simplest one. There's lots of ways to speed this up with approximations and vocabulary trees and all sorts of other things. I'll describe some of that later in the semester. So now we've got a set of possible correspondences, and we want to try to solve for an affine projection. So this is just showing what an affine projection models is a 3D rotation of a surface in translation under orthographic projection. I'll talk about what orthographic means later too, but basically you can think of it as that the object is allowed to get smaller, and it's allowed to shift, and it's allowed to do a 3D rotation, but I'm not accounting for perspective, which is that as points get further away, then they become closer together in the projection. So my model, we talked about this. I've got my affine projection. If I've got a set of corresponding points, I can just solve for this by racking up a 6x6 coefficient matrix, which is on the left side here, and my right-hand side vector, and then doing pseudo-inverse. So this is easy to get just by rewriting this. So you want to rewrite this equation so that instead of writing it as a mapping from one point to another point, you rearrange it so that it's coefficients times the variables that you're trying to solve for, and then another set of values that you know. So how many match points do I need here? Minimally to solve for an affine transformation? Right, just 3, because every pair of points gives me 2 equations, so 2 constraints. So 3 gives me 6 constraints, and I've got 6 variables. All right, I'm not going to be able to go through a lot of this in too much detail. So then I've matched the points from every input image to the database image. I get the locations. Then I do Huff voting. So I create a bin where I've got a 4-dimensional binning matrix for X, Y, scale, and orientation. And the bins are really wide. So the bin width is 1/4 of the object length in position. So you only have like maybe 10 by 10 bins for location in the image. And then you go by steps of 2 in scale and 30 degrees in orientation. So you're just trying to see, is there a possible rough match here? Then for every pair of corresponding points, you vote inside this binning matrix. And then for every bin that has at least 3 points, you do what's called geometric verification, which is solving for the affine transformation and seeing how many other points agree. So you have to keep track of, so basically your vote is going to consist of the relative scale of the key points in your input and database image, the relative translation, and the relative rotation. And then you're keeping track of that in a 4D matrix. Then you report an object if it has at least T inlayers. Probably actually I'd use more than 3. So here's some quick examples of this. So here it's used to match this image of a frog and train to and other objects to this image on the bottom. If you have many images, then of the object that you're trying to find, you can use all of those images. And you can also create tracks of features between those images to allow you to match match your database image to different tracked features on different input images. So if I know that if these are my training images and I know that this point matches this point and this point matches this point, then I can match from features here to both of these images and solve for a single alignment by transferring those correspondences. This is used in the IBO, which is an old robot, and it's used in lots of other applications. You can do location recognition. And so finally, there's two other alignment methods that I don't have time to go into, but they're worth being aware of. One is thin plate splines. And that combines a global affine warp with smooth local deformations so that you can, usually the example is if you think about like deforming a cloth to fit some surface or a sheet of metal, then you have some overall deformation, but then at certain points you like bend the cloth or the metal to locally apply another transformation. The other is robust non-rigid point matching, which tries to resolve the problem of bad fits due to bad local minima. So you start by relaxing the fit, and then you basically start by solving for just a scale and translation, and then you tighten up the correspondences over time until you're doing the same thing as ICP. Right, so the key concepts, we talked about the Huff transform, Mansack, and ICP for alignment. And the Huff transform was the algorithm that was used in the original object instance recognition paper by David Lowe. Great. Thanks for your time, and have a good weekend.